Right, question 6 came from a January paper. I just need to check, but yeah, it came from very likely this year's January paper. Just including the things here. Okay, now given a partition of the interval 1, 2 by this partition, they normally give you the partition, so you don't suggest the partition there. Okay, so the partition begins with 1, and then 1 plus 1 over n, 1 plus 2 over n, etc., etc. How is this partition constructed? Just in case we are not given the partition, we note that this partition begins from the number 1 because it's the lower limit, it's the lower boundary of this interval. So it begins from the lower boundary of this interval, and then you add to it. So it's the lower boundary plus I over n. Okay, right. So, and what about n? N is from what to what? Okay. So we note that n itself will run up to, or I will run up to n. So in other words, the I will actually, it's a number that's going to run from 1. Okay, so you can take it from 1, or you can take it from 0 to exactly what? To exactly n. Because when I is n, when I equals n, then you have that, you have the 1 plus, right? So you have the 1 plus, when I is n, then you have the 1 plus I over n. And then this is 1 plus 1 plus n over n, which is 1 plus 1, which is 2. Right, show that the upper and lower sums converge to the same limit. Okay, what we do here? First, we look at the function. We draw a rough graph of the function over the interval of integration. So first things first, it's very easy to draw. This one is a school grade 9 graph question. So when x is 0, you find the intercept. Okay, you start. When x is 1, you put here. So it's minus 2 plus 5, which is exactly 3. So in other words, when x is 1, y is the number 3, and therefore you have a point here, right? And moreover, when x is 2 now, you put 2, which is 5 minus 4, 1. When x is 2, y is 1. So this is the graph. Okay, from the graph, we can see that the function is decreasing. This is extremely important for us because when the function is decreasing, it has implications when it comes to the integration techniques. So we begin as follows. Right, we say we have a decreasing function. Okay, we either state that we have an increasing or decreasing function. So we have a decreasing function. Right, full stop. Having a decreasing function also right, so we also have, now since this function is decreasing, it means two things. For a decreasing function, you have the infimum and you have the supremum. Right, so the infimum, small m. So if the function is decreasing, so this one is like an xi minus 1 relative to this one, which is an xi. So the one before is xi minus 1, and the one after is xi. Okay. So this one is fxi. This one is f, this one. is fxi minus 1. Okay. So at this point is the point where you have xi, and then you have fxi. Okay, and then here you have a point xi minus 1, and then you have fxi minus 1. So which means that here at this point you have the smallest y value. Which one is smaller between fxi minus 1 and fxi? So decreasing function again. Okay, we know that already. But key to the decreasing function is the fact that we need to compare, because now we want to determine which one is the supremum, which one is the infimum. So, but we can see therefore that the f, so we compare fxi with fxi minus 1. We compare which one is bigger. Now, the biggest one is the highest one. So this is the case. So we can see that here, like here, fxi is like 1. And then fxi minus 1 is 3. So fxi is smaller. Example 1 less than 3 for y. Okay, because x is from 1 to 2. So the 1 and 3 are not at all a contradiction. They are endpoints on the y-axis. Okay. So we find. So this one is f. Right. So the xi, what is xi from the interval? So xi is 1 plus I over n, which is 1 plus I over n. So this is it. But now let's think about this. So this is a function. So you need to substitute now. So it's minus 2x. So it's going to be minus 2xi plus 5, which is minus 2. What is xi? It's 1 plus I over n plus 5. And therefore, we multiply out here. This is minus 2i over n. Then there's minus 2 plus 5, which is only 3. Okay, so this is giving us the smallest one, which is the infimum. Now, then we have the next one, which is the supremum. Okay, so continue. And then this one is that. Okay, is that? I want to write a civilized equation here. The civilized equation would be the function is minus 2x plus 5 to be integrated. So we will have here minus 2x I minus 1 plus 5. What is xi minus 1? So xi is the point from the partition. So which means we have xi minus 1, which is 1 plus I minus 1 over n, which is 1 plus I minus 1 over n. So which is minus 2 into I minus 1 over n, which is plus 3. So hence, now we want to find the lower sum, LPN. So LPN therefore becomes the summation from I equals 1 the lower one plus 3. Now you take 2 points here. Now, okay, this one is delta xi. So, but you need to take 2 points and subtract them here. Maybe this one and this one. So if you take 1 plus, it doesn't matter which ones. Okay, you take the next one, subtract the preceding point, and therefore you get 1 over n. Even if you take this one, you're going to get 1 over n, etc. So it means delta xi is 1 over n. And the implication, therefore, is that this summation over 3 over n plus 3, so delta xi is 1 over n. Okay. And then now we just need to expand this one. So it is the summation I equals 1. So which is minus 2i over n squared plus 3 over n. Okay. LPN, which is the summation okay, I equals 1. Then I'm just copying this one. Minus 2i over n squared. Three over n. Okay, let's continue. So what do we get here? Okay, now here we note that the rest of these are constants. The only variable is I. So if I want to perform this summation, I can take out the constants and just deal with and perform the summation of I plus the 3 over n, which is the summation of 1. Okay, what is the summation of I? The summation of I is 1 plus this is a sum of the natural numbers from 1 to n. So from school is an arithmetic series. 1 plus 2 plus 3 is an arithmetic series with a common difference. Okay, that said, we know that the sum of this, we did it last time, is n into n plus 1. So I'm going to give the formulas of the sums up to cubes when you have higher order things to integrate. And therefore, this one here, out of 2. is 3 over n times n. Okay, because now we're summing 1. 1 is actually n by 1. So the summation of 1 is n by 1. Okay, so we have that. N by 1. N by 1. Okay, so now let's just simplify this one. Right, simplifying these, the 2 cancels, the n cancels, leaving us with minus n plus 1. Okay, so here you have minus 1 over n. So the answer is 2 minus that. Okay, so in other words, hence the lower Riemann sum is given by LPN, which is this. Then you have UPN. Right, so UPN therefore is the summation of, okay, you can start here, big MI for the supremum times delta XI. Simultaneously, I mean, it must be noted that here, this one is also the LPN. It's formula from first principles, just basic. Okay, if you this small mi is the infimum delta xi. So this one therefore becomes the supremum. What did we get the supremum to be? Previous page. Right, the big M is found to be this. Minus 2 that. Minus 2 into I minus 1 over n. So this one is minus 2 into I minus 1 into I minus 1 over n plus 3. Okay, over n plus 3. Right, and then you close the bracket. Finding the sum. Okay, now let's just expand. We just need to evaluate this sum here. Right, so we can just multiply out everything within the brackets. So it's minus 2I over n. Right, which is plus 2 over n. And then we also have 3 there, which is with this. Right, so, okay. You know, there's always a pattern in the way these sums are sort of work out. They'll always differ by a sign. This one is 2 minus 1 over n. The next one, the supremum or the UPN must be 2 plus 1 over n, because there's just sometimes a bit more work, so there's always a chance of human error. So you can find that one commits a mistake. Right, so to avoid certain mistakes, we note the patterns. So here, this one, we can see that minus 2 over n is a constant, this one. We have this one. Plus 2 over n with this one. plus now the 3 is also a constant, so you can take it out outside the summation. And then you just sum 1. The sum of 1 is a constant, so if you're summing a constant, which is minus 2 over n. Okay, the sum of this one is over 2. Which is n by 1. N by 1. Did I do the other one well there? See? Let's see. Ah, I forgot. Right, remember that there's delta xi. You can see something is missing here. So delta xi is 1 over n. Just include it here. Right, it's 1 over n. So let me just remove this. And see that something is just not adding up. So we must multiply by the delta xi. And then we can find the sum here. Okay, so first things first, we multiply through by the 1 over n outside for the delta xi. Right, so this is minus 2i over n squared. Plus 2 over n squared plus 3 over n. Okay. So which is minus 2 over n squared. Okay, I'm just checking if everything is well. Okay, it looks okay. It's like I missed nothing. So you have n squared, which is a constant. The only variable is I. So you have this. 1. The 3 over n is also a constant. And then you have 1. Okay. So now this one is minus 2 over n squared, which is n, the sum of the first natural numbers, the first n natural numbers is exactly that. So you have that squared, and then here you have 1 by n, and then here you have 3 over n, and then here you have only n by 1, like this. So this is the same as what? The 2 cancels and the n divides. So you have minus n plus 1 out of n. Okay, it's integration. So at the end of the day, the limits must be the same for both of these, which is 2 over n plus 3. And then what is this? So now it's minus 1 over n plus 2 over n plus 3. So now this is 1 over n. So this one is 1 over n plus 2. Okay. Most importantly, it is 2 plus 1 over n, which is the correct one because it must just normally differ by a sign. This one. So um, we have this. So hence the UPN, which is the upper Riemann sum, is 2 plus 1 over n. Is the upper Riemann sum. Okay, we've already found the upper and the lower Riemann sums. What is it? Show that the upper and lower Riemann sums converge to the same limit. So obviously, if they converge to the same limit, we must just take the limit to prove the convergence. So we'll take the limit on the next slide. So that's LPN, which is this, in UPN, so that the limit normally is Kelly. You can write like this. It's L Kelly N or script L, yes. And then you find the limit as n approaches infinity of LPN. Or you can only write, okay, LP, L of P. Right, so this is the limit, n approaches infinity of the LPN, which is 2 minus 1 over n. And this is the same as 2 minus 0. 1 over infinity is 0. So 2. And then here you have this one here. It's a tricky U that to write that one. Is some Kelly U or some sort of script U. Okay. So here's some script U to write. So you have some script U here. The limit as n approaches infinity of UPN, which is the limit as n approaches infinity of this one. Yes, please, my dear. Yes, my dear. No, what's the color? Yeah. No, if Vaseline, I don't know. Okay, I'll come and take that. Okay, thanks, my dear. All right, so you have this one, which is exactly 2 plus 0, which is 2. Okay, so we have that the lower sum is 2 and the upper sum is 2. Um, hence, L is U is 2. So that they are equal this. So that the upper and lower Riemann sums converge to the same limit. So that the upper and lower Riemann sums converge to the same limit. So that we infer that we infer that the upper and lower Riemann sums converge with the same limit. Okay, so we have answered this question. But they asked that question for 11 marks this January. I think it was this January supplementary exam. Okay, they asked the question like this, but I need to state something that obviously we can find the integral of the function f. Okay, because whatever we found is actually the integral of this function, f of x, which is minus 2x plus 5, when x is an element of the interval from 1 to 2. So, um, we know that. We know that the integral of from 1 to 2 of the function f of x dx. Okay, this integral of the function determines the area under this graph. And that's what the integral means. But obviously this notation for the integral sign represents the summation to infinity. So, which means that the function is this one, minus 2x plus 5 dx. Let me put an easier function to deal with. Goodness me. So we have 2x squared over 2 plus 5x from 1 to 2, which is minus x squared plus 5x. And this is minus 2 squared plus 5 by 2 minus 1 squared plus 5 by 1. So this one is what is 10 minus 4, 6 minus, this one is 5 minus 1, 4. 6 minus 4 is 2. Okay, and this means the integral of the function of x is equal to 2. Obviously, it agrees with the method of partial sums. The method of partial sums, and obviously the method of what we call the Riemann sums, the Riemann upper sum and the Riemann lower sum. And obviously the fact that the integral is 2, but we need to use the sums, but I was just doing it here to verify that our answer is correct. Now, there's something we need to just as well reinforce the next concept, which is the idea of the left-hand derivative we looked at last time, but now I just applied to a different question. So yeah, this is not at all difficult. It's normally very, very easy to do once we just master that one. Right, so one can be rest assured to get 100% in this coming exam for this module. Not at all difficult. But now, for instance, now let's deal with this. But first things first, it becomes so important to look at this one here when x is 2, which means therefore you have f of 2. F of 2, which is 10 minus 2, which is 10 minus 2 squared. 4 by 2, 8. 2. Right, so need to do this one first. All right, because by using the definition of the left-hand derivative and the right-hand derivative of f at the point x equal to 2, determine if f is differentiable at x equals 2. Okay, differentiability, we just do the left-hand derivative and then the right-hand derivative. But we're using the definition of these derivatives. But I must indicate that this is too obvious because we can do the derivative straight away. What is the derivative of this function here? The derivative of this function, the derivative of 10 is 0. Minus 2x is minus 5x. 5. And then x is less than 2. So this is the derivative of the function. So at 2, at x equal to 2, you can just substitute. F primed at 2 is the same as minus 4 into 2 if x is bigger or equal to 2, 5 if x is smaller. And so this derivative is just minus 8. Right. These are the answers we expect. X greater or equal to 2, x less than 2. All right. That said, we continue now to just use, but we already know the answer. So this function is not differentiable. It is not differentiable for a variety of reasons. It's not differentiable simply because if you look very carefully, the right hand derivative and the left hand derivative are not the same. So one is minus 8 and the other one is 5. So the function is not differentiable. By using the definition of the left hand and right hand derivative of f at the point x equal to, determine if f is differentiable. Okay, we need to determine if, but it's already not differentiable, but we're going to do it from first principles. So we start. It becomes f, the top one is the right hand derivative of the function at 2. Derivative. And this is the limit. As x approaches 2 from the right, so you have this. So you have this. So what is f of x? When x is greater, x approaches 2 from the right. So if x approaches 2 from the right, it means we're dealing with a part that's greater. And that is 10 minus 2x squared minus right. And then now we have the f of 2, which we've already got. F of 2 is 2. That's why we need the f of 2 because it's just going to be substituted there. Okay, this is like the average gradient with the limit. So we have this one. X approaches 2 from the right. Okay, we have 10 minus 2, which is 8, minus 2x squared over x minus 2. So you pull out minus 2. So x approaches 2 from the right, which is x squared minus 4, x minus 2. So with the limit, so this is x minus 2 into x plus 2. We divide by x minus 2. So which is x plus 2.
Hello.
Okay. Yes, please.
How did you get this? The minus 4.
Okay, how do I get minus 4? That's a good question. I factored out minus 2 from the numerator. So in other words, from this expression, from that expression, I factored out minus 2. So obviously what we have is we have 8 minus 2x squared. And then I can write it as minus 2x squared plus 8. And then I can pull out minus 2 as a common factor. And if we do that, it becomes x squared minus 4, okay, which is exactly that. All right, but obviously x squared minus 4 is a difference of two squares, which is x squared minus 2 squared. The difference of two squares, a squared minus b squared, is a minus b into a plus b. This is x minus 2 into x plus 2. Okay, so we have that, but obviously we have the cancellation there, and then now we have this one. Now we do the next one. We're going to do the left-hand derivative. Right, the left-hand derivative is f sub minus of 2. Derivative primed, and therefore it is this one. X approaches 2 from the left of f of x minus f of 2. We divide by this. X approaches 2 from the left. What is f of x when x is smaller than 2? When x is smaller than 2, f of x is 5x minus 8. And then you have x minus 2, which means x approaches 2 from the left. Minus 10 over x minus 2. Now here we can pull out the common factor from the numerator. We want to simplify this so that we can be able to evaluate this limit. Pull out 5 from the numerator. And have this. Which is 5. And this limit is 5. Okay, we have seen therefore that thus if the left-hand derivative is 5 and the right-hand derivative equals what? Minus 4. Okay, the 5 and minus 4 were already obtained. Minus 8 here. They made a blunder here. Okay, this is 2 plus 2. 2 plus 2 is 4 by 2, 8. So this is minus 8. Okay, so I was assisted by the fact that if you look, I already have computed the through the shortcut at the top here. So since I've computed through the shortcut, then I can see it must be minus 8. For the f plus and the f minus must be 5. So here must be minus 8 here. Okay, so we have that. So it must be minus 8 here. So we're 5 minus 8. And these 5 and minus 8 are obtained by just differentiating the function given directly. This given function directly, this one. Just straight differentiation of this function produces the result. But we have the left is 5 and the right is minus 8. And that's so that f prime at 2 is different from f primed at 2 from the right. So these derivatives are not equal, so that the function is not differentiable. Hence, f of x, okay, determine if f. So the very correct language we can use here is to say the function f, because the function is a set. So the very correct language would be to say, hence f is differentiable. It's not. It's not, because those are not equal to each other, so it is not. So it is not differentiable there. Right, so f is not differentiable at x equals 2. But it's not differentiable at x equals to 2 because the left-hand derivative is not equal to the right-hand derivative. Okay, because you look at the question again, 4.1, they said by using the definition of the left-hand derivative and the right-hand derivative of f at the point x equals 2, determine if f is what? Is differentiable at x equals to 2. We've seen it is not. Okay, I've included question 4.2 as part of what came in one of the January exams, either this year or last year. If f is Riemann integrable, okay, is f Riemann integrable on the interval -3 to 1? Okay, explain all your reasoning for 3 marks. Now, what do we do here? Is it Riemann integrable? Well, there are a couple of things that you need to consider here to answer this question. Right, and they stem around the actual properties of Riemann integrable functions. Right, and what is a Riemann integrable function? What is a Riemann integrable function? Right. Right.
Hello.
Yes, please.
Do you need the answer for 4.1 to answer 4.2?
Yes, that's a good question. Do we need the answer for 4.1 to answer 4.2? Okay, and here is the condition. I want to just give the condition. Right, so first things first, a bounded. A bounded, a bounded function on a compact interval. Okay, this is closed and bounded, and therefore these intervals are called compact in mathematics. Okay, we're gonna see that when we do 3711 compact spaces. Right, a bounded function on a compact interval, on a compact interval AB is Riemann integrable. Is Riemann integrable. If and only if it is continuous if and only if it is continuous almost everywhere. This is a very quite an advanced, wholesome definition of the this. Right, everywhere. So this is what we learn in this topic. Right, so we are effectively then saying that the function itself is said to be Riemann integrable. Right, is Riemann integrable. The bounded function of the compact interval AB is Riemann integrable if and only if it is continuous almost everywhere. Okay, this is enough, but I want to mention this. So, if and only if necessary and sufficient condition is continuity. So, is F Riemann integrable on the interval? So we require that the function be continuous. If the function is continuous over this interval, then it is Riemann integrable. But is it continuous, this function? So we need to use the answer from the previous one. You said you're right. But what did you got from 4.1? We know that. We know that this function is what? It's not differentiable. We know that f is not. Is not differentiable at x equals 2. Okay, since a function is not differentiable at x equal to 2, okay, we know that the function is not different. Put a full stop there. Okay, I want to mention something else. Differentiability in mathematics. Can you write it here? Differentiability of a function implies continuity of a function. Okay, so if a function is differentiable, then it means it is what? It is continuous. And then you can look at other negations and other contrapositions of this statement. But we know that this function is not differentiable. So, but you see, if it's not differentiable, then we have nothing to say about continuity. But if it happens to be differentiable, then we know it's continuous. So we needed this answer. But it's not enough because it must be differentiable for it to be continuous. And then if it's continuous, we just require that the function be continuous for it to be Riemann integrable. So the question is, can we be able to extract continuity of this function? Because we want continuity. But we can't now obtain it from differentiability because it is not. But if it is not differentiable, it does not mean that it is not continuous. Because since f, I'm just writing these things. Since f, okay, the answer is already there. But since f is not differentiable, it doesn't follow. It does not imply that. Which am I writing here? Okay. Since f is not differentiable, um, we cannot we cannot infer that f is not continuous. So we can't say it's not continuous because it's not differentiable. Okay, I don't want to write an essay here, but I'm trying to say a very good example we learn in mathematics is the absolute value function y equals the modulus of x is continuous at x equals 0, but not differentiable. But not differentiable at x equal to 0. Okay, it's continuous at the origin, but it's not what? It's not differentiable there. It's continuous at x equal to 0, but it's not differentiable at x equal to 0. So a function can be continuous and not be differentiable. So if it's not differentiable, does not mean it is not continuous. The absolute value function is a good example. Okay, I don't want to speak for the whole day about this, but I want to just give the answer to this. So the question is, with all this knowledge, then we can give the answer. What is the answer? Well, the answer is to say, is this function continuous over this interval? So we need to analyze the continuity of this function. Okay, so first things first, you need to infer, you need to know, is this function itself continuous? Okay, because the point 2 is outside this. Okay, I want to say that it's not differentiable at x equal to 2, but x equal to 2 is not part of this interval. So we're here. It's not differentiable there, but when you look at when x is less than 2, what part of the function is this? Is this straight line? And this straight line here is clearly a continuous line. This is a continuous line of positive slope. The continuous line of positive slope when from 2, it's a continuous line of positive slope, whatever the graph. So something of that sort. Okay, we're done with this question. So the answer is that this function is continuous here. It's continuous there. So I'm gonna write the answer to the question. It's not everything. We've just written too many things here to create. So I'm gonna write the answer in purple. Could use blue maybe. Is f Riemann integrable on the interval? Yes. F is Riemann integrable. Is Riemann integrable on the interval. That. Yes, f is Riemann integrable on the interval that. Since f is continuous. It's continuous on the interval. On the interval minus 3, 1. Okay. I just picked this paper randomly for us to discuss from my past exam collection. Okay, but now, yes, so this one is Riemann integrable on the interval since f is continuous on the interval that. Okay. How do I know that f is continuous on the interval? Once again, I said between minus 3 and 1. You can see that it's 1 to minus 3. So it's less than, both numbers are less than 2 and less than 2x less than 2. You have a straight line. The straight line is continuous. Continuous means that does not have a break. So this one has no break. The point of discontinuity here is outside minus 3 and 1. So we're done with this question. Okay, we'll move on. Right, the next thing we're going to look at is question 3, and we're looking at more series now. Right, so in view of the series, show that the series, this one is divergent, and explain your reason. And explain also your reasons. Okay, you need to show that this one is divergent. How do you show the divergence of this series? Right. There are a couple of things you need to consider to show the divergence of this series. Right, so we get started now. Right, the question becomes, what test is applicable here? So there are a couple of tests, but the question is, which one is the most applicable test for convergence or divergence of this series here? Right, so we analyze that part. Okay, so we let an be minus 1 to the n, the square root of n squared plus n minus n squared minus 1, which means this. Okay, which means you have this one. N squared plus that minus, so that, goodness me, we'll continue. So that now this modulus of an can be, we can rationalize this. N squared plus n squared minus 1 which is n squared minus 1 n squared minus 1. Okay, so when we multiply this out, n squared plus n minus n squared minus 1, which is n squared plus n plus n squared minus 1, which is the same as n squared plus n minus n squared plus 1. Okay? N squared plus n plus n squared minus.
Hello?
Yes, please.
I'm confused what's happening here.
Okay, I'm rationalizing. That's a good point. I am rationalizing, so I'm just multiplying by 1. Right, so right, multiplying by 1, like normally if you have in mathematics, we rationalize. You can rationalize if you rationalize anything. Like if I say the square root of x minus the square root of 5, how do you rationalize this? Which is this? So we have this. So now you multiply everything here, it becomes x plus 5. Okay, so we rationalize like that. What is the purpose of rationalizing? Well, because we can't deal with the problem when it is in this form. In particular, we can't deal with this because this is the sum to infinity. So this minus is problematic. We want to change this minus to a plus, and we must rationalize like this. Hence the modulus of this would be, from this, it follows therefore that the n squared minus n squared is 1, is 0, leaving us with n plus 1 n squared minus 1. Okay. All right. I wrote it too low. Let me write it here. Which is n squared plus n plus the square root of n squared minus 1. Okay, I'm removing this one. Can you use the vanishing condition? Right, the vanishing condition here is what we use. The vanishing condition is what we use here to find the limit of this. Okay, it looks very, very palatable. So we have now sequences here as part of the problem, but then we need to find the limit. So we have the limit of this, of the modulus of an, which is the limit of this one. You can even remove the absolute value out of the n plus 1 because it's already positive, but it doesn't matter. Can still maintain it. Um, one plus 1 over n. Okay, then you pull out n from the numerator. And then you pull out n from the denominator, which is, if you pull out n, but under the square root, you pull out n squared. And here you pull out n squared. Okay. So you have 1 over n plus 1. You cancel 1 plus 1 over n. Whereas n approaches infinity, the numerator is going to be 1 because 1 over n is a null sequence. And then 1 plus 1, which is 1/2. And 1/2 is not 0. Good news. Once this is not 0, then you celebrate, because if it's 0, then you cannot use the vanishing condition because it vanishes already. Vanishing condition means the function vanishes. The limit of the sequence vanishes. The limit of the sequence itself vanishes. So this is the conclusion. So the limit is 1/2, which is not 0. Now since the limit is n approaches infinity, of the absolute value of an is not 0. This limit is not 0. The implication is therefore that the limit of an is n approaches infinity itself is what? Is not 0, this limit. And from the contrapositive, I spoke about the contrapositive. I'm gonna just, I'm yet to spend a lot of time on the contrapositive inverse and those kinds of things. So the converse and all that, negations and complements. Right, and from the contrapositive of the vanishing condition, okay, the summation.
Hello?
Yes, please.
Why did you do this step?
Why did I do that step? I did that step to evaluate the limit. Because now, you see, if I take straight away the limit and I substitute infinity straight away here, we're going to have the indeterminate form infinity over infinity, which is indeterminate. So I have two ways to evaluate these limits. I can factor out n, or we can use L'Hopital rule. because we want to find this limit here. What is this limit? So I decided to factor out n is the easiest thing. If you factor out n from the numerator, that's what you get. If you factor out n, now factoring n from the denominator is a little bit tricky, but yeah. Because if you have n squared plus n, you must factor out, you have the square root of this. So you must factor out, n squared from this. You must factor out n squared, and if you do, it's 1 plus 1 over n. Factor out n squared. Because if you multiply through by the n squared, then you're gonna get that back. And then take the square root of n squared, which is n, and then you have 1 plus 1 over n. And the same is done for the other one. So that is how, but now then you factor out the n that is going to come out of this and factor out the n that's going to come out of the other part. Okay, obviously we agree that this n is going to cancel this. Okay, and therefore the limit is 1/2. But I'm writing the conclusion at the top in red, and I'm saying since the limit is not 0, or of the absolute value is not 0, and the limit of an is not 0, and from the contrapositive of the vanishing condition, from the contrapositive of the vanishing condition, this series of -1 to the power r can use n from n equals 1 to infinity. This series is divergent. It's divergent. Since the limit is not 0 and the limit of an is not 0, and from the contrapositive of the vanishing condition, this summation is, this series is divergent. So they said show that the series is what? Is divergent and explain all your reasons. And we've shown that. Okay. Now we look at the next question. Okay, the next question is about the nth root test. Use the nth root test. So it's another test. We have seen the ratio test. We have seen the p-series test. And we have seen the integral test. All right, there's something called the nth root test. The nth root test. Right, by the nth root test, this is what we mean. Nth root test. Nth root, not roots. Nth root. So that means we have the limit of this. Okay, so this limit, you take the nth root of the absolute value of an, and then you'd have 3 cases. So the L can either be 1, yeah, can either be equal to 1. Okay, let me do this. I want to put the 3 things, 3 properties. So we can have that L less than 1. If the limit is less than 1, we have convergence. Oh, yeah, convergence. But if the limit is bigger than 1, then we have divergence. And also the limit can be 1, inconclusive. So the test does not work. So it means you must try another test. So, okay, here they suggested the nth root test. You expect it to work. Use the nth root test and show that the series is convergent. So to this here. Okay, so now we're gonna let, here's the solution in green. We let an be 2 n plus 1 to the power 2n. We divide it by 5n squared plus 1. You raise it to the power n. Okay. And then, okay, doesn't really make a difference here because this one is just a series of positive terms, but you can take the absolute value of these in view of the actual definition. But obviously here it is the same thing. So you have 2n plus 1. To the power n. Okay. We can start here. Thus, this was written recently, this paper, January, I think February, something like that. This year or last year. So now you have this. Thus now you take the limit of the nth root of this. So you take the limit okay, so you take the limit of this as n approaches infinity of the nth root of the modulus of twice n plus 1. Right, so if you take the nth root, so it will basically become the nth root of the top and the nth root of the bottom. So it becomes the nth root of 2n plus 1. And this becomes the nth root of 5n squared plus 1. So which is exactly 2n plus 1 squared. You divide by these. Okay. There are a couple of ways to do this one, but you can just expand the top. You can still can do without expanding the top. Okay, you want to get the limit, but the problem we do what we did before. We need to, if you take the limit straight away, this will be infinity over infinity. And this form is an indeterminate form. So we don't want this indeterminate form. We don't want this. So to prevent that, we're gonna expand this and get 4 n squared. Okay, and then this one is n squared plus 1. So we have 4n squared, and therefore this one is the limit as n approaches infinity. Right, so you factor out n squared from the top, it becomes 4 plus 4 over n plus 1 over n squared. And then you factor out n squared from the denominator, which is 5 plus 1 over n squared. And the n squared cancels out. If you take the limit here, this is going to be 4 out of 5, which is 0.8 less than 1. Right, so less than 1, if the limit is less than 1, then it means convergent. So use the n through test to show that this is convergent. Right, we conclude. Hence, by the nth root, nth root test, the series is divergent. Is convergent, excuse me. Okay. So we have answered this question by using the nth root test. Right, we go to the next one. The next one is to investigate the following series for absolute convergence or conditional convergence. Right, so you need to look at this series and think carefully about it. Right, this one here, you can ask a couple of questions about it. A student who is going to try the vanishing condition, this one is going to vanish and the limit is going to be 0. So the vanishing condition is not going to work. What test can work? Can you use the P-series test? The P-series test cannot quite work. It's going to be difficult to use the P-series test. The P-series test is for polynomials. But it is possible to integrate this. We can find the integral of this. So we can use the integral test. But before we use the integral test, we must know if it satisfies the properties of this. And this must be decreasing. And it must be a series of non-negative terms. Non-negative terms. Non-negative terms. Okay. Okay. We continue. We continue just one sec. We use the integral test. I'm suggesting the integral test. I've not done this question before. but I'm just going to verify if it's going to work. Right, we use the integral test because, okay, we call this function f of x. One over x and this is the same as. Okay. Right, we need to find the derivative of this. I want us to know that us to see that this one is decreasing. One way to do that is to find the derivative of this. So find it, the first derivative. The derivative of 1 over x is minus 1 over x squared, which is already a negative term. And then you have plus 1 over x, 1/2, which is 1 in x. And then now you subtract 1, which is minus 1/2. I'm going to use the chain rule to find the derivative of this 1 over ln x. The derivative of 1 over ln x is what? The derivative of 1 over ln x. Okay, 1 over ln x is ln x to the minus 1. And therefore, if you find the derivative of this, it is the same as minus 1 ln x to the minus 2. And then you find the derivative of ln x, which is 1 over x. Right, so the derivative of that is that. So it's minus 1 over x ln x squared. Okay, these guys now are both negative. This is negative, and this one is negative. So over, so this one is negative over where x is from 0, where x is from 2 to infinity. So this is clearly a decreasing function. So it's negative x is from 2 to infinity. Okay. So we can integrate. Let's integrate. But for us to integrate, we proceed as follows. Now let's let um okay. So you can let u be ln x. Let u be ln x. Which means that du which means that du is 1 over x dx. And it means that x du is dx. Thus, we use the notation Jn is equal to the integral from 2 to infinity. Okay, 2 to infinity of the function 1 over x. So you don't put the -1 there. So we're dealing with the integral test. But we are taking the 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 part without the -1 to the power r. Okay, so we have this 1 over ln x to the power 1/2 dx. So we find this derivative, this integral using properties of Riemann integration from 2 to infinity. 1 over x, 1 over ln x is u. 1/2. What is dx? Dx is x du. Which is 2 to infinity. 1 over u to the 1/2 du. So this is 2 to infinity of u to the -1/2 du. Okay, so we get this one. We get this one here. Okay, we do this normally. Right, calling this Jn means we can call the upper limit here because this is an improper integral. So we can just use n for now. And then we're going to take the limit at the end. It's convenient that way. Otherwise, you can just keep having infinity is going to give us some problems. Doesn't matter, but it's neat like this. Okay, so it's neat like this because now we're just going to find this integral as it is. What is the integral of this? So the integral of this is u to the -1/2 plus 1, you divide by -1/2 plus 1. Goodness me, okay, from 2 to n. And therefore, this is the same as 2u to the 1/2 from 2 to n, in which is 2n to the 1/2 minus 2 to the 1/2 n. That's why. So I mean, you can look at this as exactly 2 the square root of n minus 2 the square root of 2. Okay. All right, this is what we get. This is what we get. So what is the meaning of this? What is the meaning of this? Okay, you think about this very carefully and realize what we get out of this. All right, and realize what we get out of this. Okay, now note that hence the limit as n approaches infinity of Jn, limit as n approaches infinity of 3 minus 2 to the square root of 2. This limit is infinity. All right, and obviously, since this limit is infinity, it actually means divergence. Hence, the integral diverges. Or thus the integral diverges. Thus, the integral. Thus, the integral diverges. Okay, me answer the call. Okay, yes, please. All right. All right, so we have that the integral diverges. So we therefore do not have the condition we want, because what we want, we actually want either absolute convergence or conditional convergence, but what we can see is that it is the integral diverges. I want to draw some similarities here. I'm going to mention something, just 1 minute. I'll return just now. I need to just speak this person in a split second. All right. No? Brazile. 50 rand. 50 rand. All right. Okay, we continue. Right, there's a study guide. This, if you read the study guide, for example, the study guide happens to highlight a couple of things about. I want to mention something here in passing. I want to mention something here in passing. I'm going to tell you just now. All right, I'm going to tell you just now something about this particular notion. Yes. Right. I'm going to give you the page number in the study guide where this case arises. Where this case arises, right. Where this case arises, there is integration. We do lots of integration, but the integration can be used. Okay, just 1 second. I'm gonna be with you now. Okay, I want to mention the page number where this conclusion is drawn. Okay, where this conclusion is drawn, and it's on series, and series, and series, and series, and series. It's right. Okay, because it diverges. Now, because of the divergence, then you do not have convergence. The integral diverges. So, in other words, if the integral diverges, you cannot draw a conclusion based on these tests, its implication on the convergence of this particular series. And so there is more that you can do, that you need to do, basically, to unpack these. And so I'm interested in speaking about actually what happens here. Just 1 sec, I'm just pausing that here. Okay, I'm with you now. This is something I want to mention, but I'm just I can't see it, but yeah, I'm gonna be seeing it now. Here it is. For example, okay, I'm gonna mention it in passing. If you look at page 21, this is the same question that is appearing on page 21 in the study guide. Okay, so the conclusion, therefore, if we want to test these for convergence, so we then say, according to page 21 of the study guide, we conclude. This is very important. We conclude that the series, this one, all right. We conclude that the series, that one, right, minus 1 to the r, 1 over r here, diverges. Okay, once again, this you can check for your check study guide. Page, for pages 20 and 21. Pages 20 and 21. Okay, so we have divergence. Right, so we have done this one for 7 marks. It just came from the study guide. They've just put only the power there, but it's exactly the same question. Okay, right. So if you then look at 3.3.2, you have this kind of a problem. And so now the question is, with this kind of a question, what is the conclusion on this? What kind of tests can we use to verify the convergence or divergence of these? Because this one vanishes. So now, because this one vanishes, there's something we call the comparison test. Okay, I mean the ratio test might not normally work here. So by the comparison test. Okay, we're looking at 332. Okay, so the comparison test, you're gonna see it at work here. So what you're gonna do is you let an n over n cubed, which is, you can write, okay, you can put this one, but yeah, and then n cubed, and then you have n over n cubed plus 2. Okay, so you have that one. Right, so and then choose. So you do that, then choose. You make a choice. Then you choose Bn to be n over, you take the highest degrees. So you take n over n cubed. And then you divide these, it becomes 1 over n squared. Okay, this is very creative. Then the comparison test has these implications. Then the limit n approaches infinity. The limit n approaches infinity. Of, okay, so you can call this one modulus like this. Okay. So which means now you have an, which is this. Okay. Anyway, whatever is the right thing to do here. Okay, so you have an, which is n over n cubed plus 2. Then you have the bn, which is 1 over n squared. Um, then you can write like this. And then this, the limit. So you have n cubed over n cubed plus 2. Okay, we have this. Okay. Okay. Okay, good. I'm just something. So now this one here would be the same as, what is this limit? Is 1 straight away, because you divide the top by n cubed, you divide this one by n cubed, and this over n cubed. And this also 2 over n cubed, dividing everything by n cubed, and therefore the result is 1. Okay, I'm going to mention something here about this test I'm using. This is normally called the second comparison test. Okay, so I'm going to give a statement about the second comparison test, but also called the limit comparison test. So you have those kinds of implications there. Okay, I'm going to just give a statement now of the comparison test. Right. Just a sec. I'm going to give a formal statement. Here it is. Okay. Now, there's something called the limit comparison test. Limit comparison test. It's much more solid, this one. But it has the same power as the comparison test. Can I state it on the next page? Right, I want to state it on the screen because it has a bit more theory. Right, the limit comparison test. What does the limit comparison test actually say? Suppose that. Suppose that we have two series. Okay, so we dealing with the two series, the original one and the other one that is the Bn. I said choose Bn to be something there. Well, obviously, you understand that this must be series of positive terms, so that's why I've taken the absolute value, so that An is bigger than 0, but essentially Pn must be strictly bigger than 0 for all n. We proceed to define, the C, which becomes the limit of the An over Bn. If C is positive, that is, if a C is positive and is finite, less than infinity. Okay, finite means C is smaller than infinity. Then either both the series converge or both series diverge. Okay. Now we're back here. Yeah, it means therefore, hence, C is equal to 1, which is positive. It is positive and finite. So by the comparison test, okay, by the comparison test, both series must converge. You see, both series must converge since the summation of the B. So you just need to look at the series. So here we shall look at the 1 over n squared because it's simpler. This one is difficult to see convergence, but this one is a P series. It's a P series with P equal to 2 bigger than 1 convergent. So since this one is a convergent P series. Okay, by obviously we remember that a P series, or what we call the P series test. What does the P series test say? Well, we are speaking of a series of the form 1 over n to the power p from 1 to infinity. There are three cases: either the p is bigger than 1, or p is less than 1, or p equals 1. P less than 1, p equals 1 means it diverges. Diverges, and this one converges. Okay. So this is what we have. Okay, the examples of the convergent ones, like, so we're done with this one, it's a convergent. Okay, obviously, absolute or conditional convergence, so it is absolute convergence here. It is certainly absolute convergence. Hence, the series is absolutely what? Convergent. Because we have taken the absolute value, so it's absolutely convergent. All right. We used the limit comparison test. What does the limit comparison test? So obviously, I want to just mention in passing here, there are some examples of P series. Which are, this one is called harmonic series. Harmonic series is divergent. Okay, it's called a harmonic series, but it is a P series with P equals 1 because the power is 1 there. And then there are more. Okay, I'm just going to give one now. Just a sec, just one. I'm not going to waste lots of time. I want to give another P series that is popular in mathematics. It's there in 3705, MAT 3705. Okay, the series of, just that is not popular at UNISA, that this series I studied a lot, is mostly contour integration that is studied. Okay. There's a very popular P series, this one. The summation of n equals 1, the infinity of 1 over n squared, which is pi squared over 6. Oops. Pi squared. goodness me. Okay. Okay, this one is pi squared over 6. But obviously, because the sum exists, so in other words, it's a convergent series. Okay. This is what we get. Continue. Next question. Let's determine the interval of convergence of this one. Okay, for the interval of convergence, always use the ratio test. So we let an be the ln of n over twice n. And this one to be the ln of n plus 1 over 2n plus 1. N plus 1. So now, so that as n approaches infinity, n plus 1 so you multiply by over the ln of n. Okay, can I write this properly? Okay, measuring with the absolute value. The absolute value is very necessary because you have that you can have negatives. Okay, you can have negatives here. So I'm just going to put absolute value. Which is 2n. Okay, so take the absolute value of that. And also you have this one, which is the ln n minus 2. Okay, n plus 1. So you must put the absolute value here for the ratio test. So this is the limit. Okay, here we're using the ratio test. Okay. So you divide by that. Sorry, you have this one, and then you have at the bottom. So, which is the limit? Okay. So it becomes the limit n plus 1. Okay, we have this. Okay, and then you have x minus 2. Okay. Okay, now we have this. Which is the lane of n plus 1. And then you have multiplied by the limit. Separate this. 2n over 2 into n plus 1. And then, okay, this is no n, so can write like this. This x minus 2 has no n. You can put the limit around it, but yeah. Okay, this is called the limit of a product. It becomes the product of the limits. So you can break the limit. The limit can attack each expression, each factor. So it becomes more limits. It can be many limits like that. Okay, this are the properties of limits in calculus. But now this one here, if you take the limit straight away, you need to use L'Hopital rule here. So yeah, you can't factor out anything with the log, the lean, natural log. So you find the derivative of the top. The derivative of the top becomes 1 over n plus 1, 1 over n. Okay, we continue. Okay, 1. Okay, and therefore this becomes that one. Hence, we have that this is less than 1. Okay, we continue. Continue. Now, if this is true, and that is less than 1, what does that mean? It means the following. Okay, you remember that when we're dealing with these kinds of series, we need to investigate now the endpoints. We need to investigate the endpoints. How do you investigate the endpoints? Okay, to investigate the endpoints, we proceed as follows. We must investigate now plus or minus 1. So we'll continue to say 4. X equal to minus 1. You'd have the original one, which is lean, the summation from 1 to infinity, lean over that. Summation. It is therefore the summation from r equals 1 to infinity of ln r over 2r. Okay, so we put x to be minus 1. So which is ln r over 2r minus 1 minus 2 to the power r, the infinite series to r minus 3 to the power r. Okay, so this is what we get. Yes. So what is this? This one is an alternating series because it is minus 1 to the power r. Then you have ln r Okay, this is an alternating series. It's an alternating series with um, right. So it's an alternating series with you know what I did there. Um, Did I delete the things? I think I did. Okay, accidentally. Because I can't see the things I was writing now. I think I accidentally deleted. I'm gonna write that quickly. I was saying for x equal to so we have two cases, x equal to -1. In the other case, x equal to 1. Okay, the x equal to 1 case means we have the series here. The ln r over twice r is x minus 2 to the power r. Okay, anyway. They're both alternating. And this one is also alternating. I'll be very brief now because I don't know what I pressed here. So you have that. The power r, which is the infinite series. And this is -1. The power r. Okay, so if you let Bn to be ln n, which is going to be the same thing, both cases, because they're both alternating, at 3 to the power n. What is this limit here? Goodness me. Which is n approaches infinity, which is ln n over 2n. The limit is n approaches infinity of 3 to the power n, and this is the limit here, which is 1 over n divided by 2. And therefore, this is the limit n approaches infinity of 3 to the power n. What is this here? So this is the limit n approaches infinity. Okay, continue. So this is also infinity over infinity. Okay, and this becomes infinity. Okay. Need to right. Here with you now. There's something I need to include here. Mhm. Okay. Okay, just note that. But now you're getting infinity for that part. What about this part here? If you let Bn, is it increasing or decreasing? I'm gonna analyze that. But you let Bn to be the limit of n divided by n, and this means, okay, you attempt to find the limit of this. The limit as n approaches infinity. Which is, okay, now if you divide, if you evaluate this limit now, this is infinity over infinity, but you can find it, use L'Hopital rule. The rate of the top is 1 over n divided by 2 is the limit n approaches infinity of 1 over 2n. 0. Beautiful. Now, we suspect therefore that this is decreasing this. It must be decreasing for us to conclude on convergence for the part where x equals 1. Right. The couple of ways to check that is to look at the first derivative and see if the first derivative is negative. Let's compare Bn plus 1 and Bn. So you'd have to compare, for instance, ln 3 over 2 times 3 and ln 2 over 2 times 2. This is ln 3 over 6, ln 2 over 4. What is the difference here? Which one is bigger? Because you want to compare these. Okay, right. I'm going to use my calculator here. Use my calculator here quickly. Ln 3 over 6. Okay, so we're comparing ln 3 over 6 with ln 2 over 4. Ln 3 over 6 is 0.18310. So you have 2, 0.11, 552. So it means that it's increasing. Right, so it must be decreasing for convergence. Okay, so in other words, you can't use the alternating series test because alternating series test works for it to imply convergence. We require um, for it to imply convergence, we require that it must be decreasing, which is not the case. So it's not decreasing because we can see clearly ln 3/6 is 0.18 and the ln 2/4 is 0.11. It means that Bn plus 1 is bigger, but we want it to be decreasing. So we want Bn plus 1 to be less than Bn. Okay, and it is surely at this point, it is not at all the case. Right, so we make a conclusion based on these two experiences that we cannot, there's no convergence here. There's no conditional convergence. There's no conditional convergence. But also at the top here, there's no conditional convergence. At these extreme points. The conclusion we draw is therefore that the interval of convergence, that's the interval of convergence is that one. And we're done. And now we've gone beyond the time. I watched the time there. Right, I watched the time, so we're done. And I was planning we do, okay, it's the end. Right, so I must thank you for joining us. Right, I must thank you for joining us. And so I'll see you again tomorrow. Let me check the time. Let me check the time at which I'm checking my load shedding schedule as well. All right, so you have my area. Okay. Right, so tomorrow we can meet at the same time, 4:30. If you're able. We shall continue and look at more things. We'll look at more things tomorrow. Right, we shall look at more things tomorrow at 4:30 in the afternoon. Okay. There are more things which will be focusing on other areas we did not cover, we have not covered yet. So those areas will be covered tomorrow. So be present. Tomorrow at 4:30. If 4:30 is not ideal, you can give me some later time than that. Okay, because my load shedding is going to be from 2 to 4, and then I'll be okay afterwards, after 4:30. So you can make it 4:30 if that is ideal with you. Then we're going to look at more things into real analysis, the things we've not discussed yet, more problems, practice problems. I'm going to gather more practice problems from the textbook. I wanted to gather today, but yeah, I was just looking into some past exams. The most recent one is the one discussed today. But yeah, I'm going to gather a lot. So, but I must thank you for joining us and have a good evening. I'll just upload the video in the next couple of minutes. Okay. Thank you and goodbye.